Well, I want that clip too. I'm Ron Swanson. I was fucking born ready. Because I don't think he says F because it's on TV. It's on daytime TV. Parks and Rec.
Right, right. All right. Hello, everyone. Welcome to a Tutor Wizard live stream. Yes, I guess that's how I'm opening it up. I gotta script these one of these days. I'm not
You'll
just wing
you'll converge to the limit of what you want to say eventually. So
Eventually, yeah.
we gotta let time tend towards infinity, and then Lorenzo will go to his asymptotic phrase that he uses.
Regression
Something like
towards
that.
the mean
Something
or
like that. I
something?
made that
Yeah.
shit up.
All right, so it's our Thursday stream, so we're doing something. Adrian, why don't you let us know?
Okay, I prepared the wrong thing because I don't listen very well and I don't work well with others. So I prepared the history of math, which was now moved as someone who's competent, moved it to Sunday. But we got a large peak of watchers and new subscribers from it. So then I got excited and prepared that today accidentally. But I can do, unlike most of the mere mortals out there, I can do as a wizard, I can do a bunch of integrals, and then we'll make a segue into this because I wanted to talk about calculations and the Babylonian method of approximating square roots, etc., etc. So I'm going to do the things that I just said, which I don't remember already. We're going to do integrals. Last time what I was doing integration, where I was going to do a bunch of standard functions in their graphs, and then instead of looking at their graphs and transformations, we would do that and look at their derivatives and then use those and piece those together in your mind as a lexicon for the first substitution rule in integration. So substitution rule. And I'll remind you, if you're actually dedicatedly watching these, thank you very much. And on YouTube, we just got over 2,000 subscribers. So we appreciate this, and I'm very one-directional a lot of the time, and I just focus on math. But we broke 2,000. I know this is Twitch, and I'm advertising for the wrong. It's like this is the wrong platform, but we're gonna post this on YouTube later. Two birds, one stone. So I appreciate the people. We broke 2,000. We'll have a celebration this weekend. Maybe we'll try a YouTube stream. That'll get us to
Oh,
actually
yeah.
start doing our own YouTube streams again because we actually broke 2,000 people on YouTube. But if you're watching these on YouTube, and when you're gonna post this, or whether you're live and actually watching in real time, you can always use this. We're going to try and use each of the videos as a platform, especially for the integrals or bust. I wanted to rephrase it as, instead of just randoming 1,000 integrals and not organizing it, I'm going to organize it into my lexicon or Rolodex of integrals, the techniques that I have. And so for the first ones, if you want to give me any integral you want in the next couple of videos, when I do integration or bust, we're going to do substitution rule. So try to find your nastiest substitution rule type integral instead of just giving me some random non-elementary function and saying laugh at me when I can't get it. Instead of doing that, you can still challenge me and poke at the bear if you want, but you can only poke at me, and we'll only accept submissions of the substitution rule integrals for a little while. Having said that, let's look.
Do you wanna field the question first before you jump
Okay,
into
I've
it?
got my PDF up. Just wait, I wasn't looking up at this. What do we got? Oh, from my point of view, brace yourself because you're going to get a real answer. But the abstract nonsense is extremely good. But after 20 years of trying to do that, I got an honors math degree with first class summa cum laude in honors mathematics at the University of Alberta. And then I got a pure math degree at the master's degree at the University of Alberta, and then an applied PhD at the University of Alberta. And the peaks and the heights that you get to in pure mathematics, is the analogy is the view at the top is spectacular, but no one else wants to go up to the top of Everest, and you're probably going to die right away, so get back down as soon as you can. You get the view, you get the spectacular thing, and you climb the mountain for the mountain's sake. The more applied one is the engineers ask, well, there's no real ores or anything useful from here on up, so why are you going up there? And we say, well, we're going to go up there because it's the view spectacular. So I would say applied. Everything is applied mathematics in the fundamental sense, and when I segue from substitution rule into the history of math, my focus is going to be on, if you can't phrase it in a way that we could actually look at geometrically or physically a real world problem and then try to use algebra to explain it, then I'm no longer really interested in the abstract nonsense that people try to academic gatekeep and don't let you into these big things. Most of the topics by this time are going to be algebraic topology or differential geometry or these really high-end, extremely difficult things. And so if you're into that kind of stuff and you want to spend time in a dark room, quite literally by yourself, where no one wants to care or have any conversation with you, and do go to those peaks of Everest, then I would do pure mathematics. If you want to just be smart and apply your mathematical abilities to the real world, I would focus on applied math and then get a real job and get paid and move on with your life. That's what I would do. That didn't work for me, so I'm trying. I got a PhD in mathematical modeling of the spread of infectious diseases in complex networks. So when you say spread of infectious diseases, you pay attention. When I just say, oh, I was using eigenvalues and eigenvectors in the Oscar or Perron-Frobenius theorem to guarantee that there's a unique solution to a system of ordinary differential equations with an underlying complex network of graph theory and then an adjacency matrix and a weight matrix, and then we combine the differential equations and those weight metrics to get an eigenvector and then rank who is most important or where the most infected people are. You don't want to hear about any of that junk that I just spit out, but I say I'm applying it to ecology models and the spread of or hybridization of bears, which Lorenzo keeps saying we should do, and I keep promising and then letting him down.
Yep,
So we're going to do that
story,
this summer. Or when you want to talk about the spread of infectious diseases and stuff like that, that's what's important to me, and that's what I want to focus on. So if you wait around for 20 minutes, or let's crush a few amount and I'll switch. This is the very first thing I'm going to do when we start the history of math is look at an algebraic formula, but where did they get the things from, how to think about this concretely, and then use the algebra to carry it away. Remember, Muhammad ibn Musa al-Khwarizmi invents algebra in about 600 AD. We haven't got to that guy yet, but we will. And so we invented this. We are very geometric and by nature. And then, yes, so let me read what you've written. Yeah. Basically, the math, this is why I like it, because it's the cliche, it's the language of the university. It's the language of the university.
Oh, you got into UCLA as a transfer, eh? Congratulations.
Yeah, congrats
That's awesome.
on that. Yeah, I was just reading the second half. Yeah. Again, I wouldn't ever tell any. Yeah, it's whether the young girls that say I wouldn't yuck your yum or something silly like this. But whatever floats your boat is
What?
the old. Yeah, I would. This is Lorenzo's like what? I still got the riz. But yeah, they try to tell you they wouldn't yuck your yum, which means yeah, if you like something, the other one's like whatever floats your boat. So I wouldn't say don't do it if you get into the pure mathematics. I'm just saying the
Applied math is very needed these
being
days.
in it for over 20 years, 25 years now, being in the system and then teaching in the system and being stuck as a sessional purgatory and not being able to get a full-time job, there are downfalls to this, and it's a lot easier to get a full-time job in an applied sector or the real world than it is in the pure mathematical niche that it could become. So we do the math for math's sakes, but at the end of the day, you start having to want to have a family and have kids and a house and stuff like that. And you can't build a house with good intentions, Marge. So,
Oh, wait, I don't think I have
yeah,
that
we got to
lined up.
find that
Shoot.
one with another Simpsons reference. So that's awesome. Let me start some integrals, but it's nice to actually talk to somebody that is worried about these types of things. So
Yeah, finally, discussion about math. Thank you, viewers. More of this, please.
put all my students from McEwen Linear Algebra 120 on blast, where they start emailing me because I posted the grades and all they want to know. It's like, what's my grade? It's like, you can come and see the exam next week. I don't want to see the exam. I just want to know what I got. It's like, oh my God, that's like the worst answer ever. It's like, I don't care. I'm just playing the education game. I don't want to know how to use Kramer's rule to explain the universe or anything like that. I just piss off and give me my
Kramer's rule's
grade
the
total.
best. Yeah, it's so
Yeah.
slick.
So I didn't respond to the last email. And I started this. That was like 20 minutes ago. Sorry, I won't say the names, but let's do substitution rule. Do you know any substitution? Can I put you on blast? The patient with the patient T, or is this the T test? Are you doing? Is that a stats? Did I just catch on to that?
You're thinking student T test.
Student T test. Okay, patient T test. I just made up my own goddamn
Oh,
thing.
pending. Yeah, we'll do something with that. Yep.
All right, I knew there was something. I don't know. I don't do stats. I do math. We've got
Tim
guys
does
that-
stats. I'll put a.
Lorenzo's the jack of all trades. He does both math and stats, and then Tim is our stats guy. But okay, so if you want,
Nice,
type
yes,
out
very
an integration, type out an integral. We're doing substitution rule though. Okay, trig substitution I guess is one. I'll allow it because it does just turn into trigonometry. Put an integral in the chat if you want, and then I'll get Lorenzo to do it.
I'll put the link to our.
Oh, the
our
website, and then
portal.
it
Yeah,
has
we can
LaTeX
type it
in there
LaTeX,
automatically,
yeah.
and you can put it in there.
1 second
Oh,
here.
good job. I can't believe the semester starts again next week. I thought that was 2 weeks from now. So I had to make all my course outlines and approve my classes. So I'm teaching calculus 1 twice, 1 in 6 weeks and 1 over the whole summer. And then I'm teaching graph theory. And I'm doing, we got approved. It's a go. I just made the website for it. We're doing
Nice.
independence research
like it.
study with Siobhan. And so I'll have to do that this time, and then we'll definitely do some videos based on. It has to now be because Mark signed on to it. It has to be. I'm bummed out because I have to do non-Euclidean geometry with Mark Solomonovich. I don't know where my head's at, but that's an awesome thing that we're gonna do. But I did want to do finite group theory as applied to cryptography and coding theory. But what are we getting?
No, don't mind me.
Hi.
Keep talking.
Yeah. Are you?
You just keep going. Don't
Okay,
even
okay.
just ignore that I'm here. Just do whatever.
Yeah. Okay, I'm going to start with one of them. Let's do an integral. I'm going to cut myself off. But we're also doing, anyways, I got my grades and stuff ready.
Long story short.
We can cut off half of this. Okay, let's do an integral. So
Eating it all.
we have a function which is a to the x. I don't know if I did this one last time.
Okay, so just really quickly.
Yep.
Twitch, right?
Yep.
And then right here, questions will pop up here.
Okay, yeah.
Okay.
Yeah. Yes.
So they'll let
Yeah.
you rearrange that.
How I want.
Not liable if it drops.
Oh, I see. It fell from like the chair the other day, and then it was weird when I restarted, and I was like, no, don't. I need you. I don't need computers or nothing. And then as soon as you drop one or something, it's like, oh no, my life, my whole life. All right. Oh, now we're gonna go down this tunnel. In particular, see, when you have slides, you become like as an instructor pedagogically, you just become like this monotonic wet paper bag as far as I'm concerned. I don't know how you get excited making pre-made PowerPoint slides and then just going in there like a slog and doing it every time. I want to tell a story. I want to tell a story about substitution rule. Substitution rule, you should get familiar with the function and its derivatives. I picked arbitrarily the exponential functions because when I was thinking last time, I don't think I did this one. I did a transcendental function. I did logarithm, which was possibly this one, I think, or I did arctan, something like this. I did the natural log and arctan. So now let's do the regular functions. And last time what I did was I used implicit differentiation to show that the derivative of arctan was 1 over 1 plus x squared, and then we used that fact to get the lexicon that the integral was this guy. And then now in particular there is, let's do the definition of, so now I want to tell the story about this function, but in particular there's a special function. Okay, so now we're going to do some calculus that I wasn't expecting to do, and if I had made PowerPoint presentations, is my point, this never would have come up, and you wouldn't just see how in the real world, this is how math comes out. If it's not in a textbook and organized chronologically, it's in this crazy person's brain and I have to regurgitate it for you. So this is what it looks like. And I'm gonna do this function. Who's this one? That one's 3 to the x. And this one is, there's gonna be a magic number e to the x. And then there's another one where I'm going to have, go Oilers. Did they play today? Or was that yesterday?
No, I'm not too sure.
I don't know. Both of us don't know. Go Oilers. I'm in Edmonton, Alberta, Canada, and I was born and raised in Alberta, and I should care about this more. I bled blue and orange when I was younger. Oh, you can't see it, but there's an Oilers Where is it? Can I keep the three frogs? Things are gonna crash. I've got an Euler's Rubik's Cube. Can we see that? It's got some spider webs and some frogs on it, but that's okay. That's all right. We can share. Go Oilers.
So our good friend Sensation Black sent a question. Now it's not in the typical
Uh-oh,
format.
what has he done?
Yeah, you'll read it in a second. So you might need to refresh the page, but you should see it. Have you hydrated today? Even soda pop counts.
I approve this question. I don't know what that means.
So
Marking is complete. I confirm this. You got yes.
you get a cookie. It's a figurative cookie.
It's like I'm hiding it up here. Oh, you didn't think I would be able to produce it. Here's the Pepsi that I drank already. And then yes, we got coffee. So soda pop and coffee. These are the three major food groups. Don't you know? Candy canes, candy corns, and syrup.
There you go.
That's
it was a very good question.
And I like
you.
Elf.
you,
Thank you,
Frank.
Sensational Black.
And
I'm
yeah,
never
it
going to
is-
get to integrals or the history of math today. Okay. So we noticed that every exponential function a to the x where a is positive. In the chat, can you give a question, or in the thing that we have, we can post it after. Why does a have to be positive?
Yes, these will be questions that we'll post on YouTube on our quizzes there on our community section. So check that out for the quiz
Or y equals a to the x.
with the question and answer.
Yeah. Why does that have to be positive? Or rephrasing it, ask yourself, I'm saying, why does it have to be positive? That means something's going to go wrong in your mind. If you're trying to think about how I think about this, that immediately rephrased as what goes wrong when a is negative. That's how you analyze this. What goes wrong when, now I'm just starting to answer it, when a is less than 0.
You could answer it if you want, and people who watch the video will get the answer. to
Okay,
the
here,
question.
I'll give a hint. That spells lint, not hint. That spells lint again. Hand. Hint, lint. Lint is I'm going to lend you an idea, but I'm not going to give it to, yeah. No, the base is negative. The base is negative, base. So yes, my hint is take the exponent, exponent 1/2, and take base -1. Uh-oh. Something's going to go wrong. You get the invention of a new kind of number, just like Cardano and Tartaglia. No G. It's silent.
G is there.
It's
it just
silent.
changes the sound. It's not even silent. It changes the sound of the
It's
L.
not for the
right?
heathen barbarian hordes who bastardized the Latin Romantic languages and the Huns language and called it English. It's not for you. It's for us sophisticated folk. Tartaglia. Anyways, that's the guy.
Bravissimo.
Okay, good. I thought I'd get an approval. Now, what I want to do is some calculus. In calculus, the slope of the tangent line to any one of these curves, so all the a's are positive is what I'm thinking, and then the slope, each one of these is going to go through the point 0, 1, which means a to the 0 is equal to 1. And so immediately, if I'm defining the logarithm, if I call y equals a to the x, and then I have the inverse, if and only if that means that log base a, we have to call it of y equals x. And then now I do it right here. I'm doing another tangent, pun intended, for that one. This one says that what I would get, log base a of 1 is equal to what? You get the values of the inverse function when you can't solve algebraically from the definition of this is the definition of inverse. But they all go through 1, 0. And then they all have to have a tangent line to the curve. And what they want is they want the curve y equals e to the x with the slope of the tangent line exactly equal to 1. Because all of them go through there, and there has to be a number. And so what they did was they checked when the base is 3, you get m of the tangent is approximately equal to 1 point, I can't remember, it's either 0, 1 or 1.1 something. Just slightly more than 1 is the point. The numbers never stay in my head. I don't understand numbers. Me fail numbers? No, I just do math. And math doesn't mean numbers. It means what was learned, what was learned from the universe. Philosophy literally means the love of knowledge. Mathematics translated is going to be that which was learned, not memorizing numbers. The tangent line here, I will do random tangents. I'm going to get Tangent Cam like that other guy that does Just Ask Joe, or that guy that does all the really good videos. He has a tangent cam and then he looks right into it and it's like, oh, I want that specifically just for my freaking, every time I do tangent, I do math and we're talking about tangent line specifically. This is 0.99, et cetera, et cetera. So they come to the conclusions, the mathematicians, practically speaking, for the patient T, there must be a function, therefore, E, we're going to call it base, where we have now that 2 is less than E is less than 3, specifically. And it has to be such that the tangent line is exactly equal to 1. There will exist this type of number. This is a little wavy hand. We have to use Cauchy sequences or something like this eventually to show that it converges to this value and get its decimal expansion. But we'll spare us for now. I'm not doing either of the things I prepped. PowerPoints are stupid. PowerPoints are stupid. Watch what you can learn from just a random dickhead talking about math because he likes it a lot. Definition. I'm going to get to an integral eventually, but I want to take the derivatives and then get there. So we're going to have to do...
We're still in the history of math.
Anti-differentiation, yes. We want John Napier is the one that comes with the E the first. I like John Napier because...
There we go, we got some history.
Yeah, he knows the story because I tell it every freaking time. I can't help it. He's also the one with the rooster, the black rooster, where he coats the rooster in soot. I can't remember the story as well, but then he gets all he thinks people are stealing from his farm, so he gets them to go in there and then touch the rooster, and whoever doesn't touch because the rooster can tell who's a criminal, but then he just powders the rooster with charcoal, so then whoever the guilty party is doesn't want to touch the rooster because they're all superstitious and they actually believe that the rooster can tell who the bad person is. So whoever comes out of the barn without the black soot on their hands has to be the one who stole stuff. John Napier did that too.
That's pretty clever.
If you think all of your employees are idiot superstitions that think a chicken can tell the truth, that's kind of degrading, but okay. And the other one was he was a rich aristocrat, segue into the other story. He was a rich aristocrat who used to like to lean on his servants, and then he had another adjacent farms, etc. And so one of them was a guy that did pigeon messaging. So he has all the pigeon coops and the pigeons keep crapping on that side of the farm or the barn or whatever. And John Napier doesn't like this. So then he, as a British aristocrat, he goes out there and says, "How dare you, j'accuse." And then the other guy says, "Well, screw you," because he's also an uppity, richer British aristocrat. And so he says, "If you can get rid of the birds, you can do whatever you want with them if you can catch them." So then he comes out the next day and all the birds are dead. And he's like, "How the hell did you do that?" He's not even concerned more about the birds at all either. Point. But he just wants to know how the hell he did it. And he says, "Well, I took a sack of grain, I took 150 proof alcohol, put it into the grain, dead birds." They all died of alcohol overdose. So that's how John Napier got rid of his stupid neighbor's pigeons. He also has the number one longest computation in a row of any human known in our species ever. It took him 25 years and he made the logarithm tables. The ones that we still use. I've got one somewhere. If I prepared, I would frickin' know where it is. This is not a logarithm table. This is my grandma's old... Oh, it is a logarithm table. Somewhere in there. He did that. No, that one's not a logarithm table. All right, definition. After we tell the Napier stories. And I'm going to hydrate because Sensational Black says I got to stay hydrated.
It's very good advice.
Except... No, I don't. I'm not that kind of doctor. Want to play doctor? No.
No.
I think
coffee.
I think coffee is an anti-diuretic. Yes. Yeah. That original story comes, I think, from John Napier, or the story is made up. So, but the pig squealing, I don't know how you conclude at the end that if the pig squeals or not. With the chalk, it just is obvious because the guy didn't want to touch it, and so his hands wouldn't be black, and everyone else that wasn't guilty just goes in quickly and touches the chicken and goes, "This guy's crazy. Why is he making me touch a chicken? I'm having you for dinner later, you stupid chicken," or "at me out." That chicken's a rat. Definition. The let the number e is such that the limit as h approaches 0 of e to the h minus 1 over h is exactly equal to 1. And then what I'm going to do with that guy, this now, is show that e is its own derivative. And then I'll use the chain rule and the definition of this exponential function to find the derivative of all of these things. Then we can get the antiderivative. But first of all, what I want is the derivative of any one of these guys so that you can see it in there. And this is one of the ones where I don't think it works good for my substitution rule business because, oh, it does. It does. I was going to talk myself out of it, but you just have to come up with a more clever, which I just did. Yes, okay. My specialty is differential equations. I have a series where, do I do differential equations on that? I do undetermined coefficients and variation of parameters in my multivariable calculus ones.
I'll post that right away.
Yeah, we'll post that right away. You can go in there and talk about it. I tutored somebody from the U of A and from the University of Regina this semester on ordinary differential equations. And so I just did the whole thing. Let's do the frickin' Frobenius method, which is out of control. Cauchy-Euler is also called, superposition is okay. Cauchy-Euler is also called equidimensional if you're looking for some on Dr. Google. And the variation of parameters and undetermined coefficients are used for all of those things. Those are the technique used to find a particular solution to the non-homogeneous scenario of the second order non-constant coefficient or constant coefficient second order ordinary differential equations. So yes, I want to do that. Check it out tonight, tomorrow. If you come back, bring your questions and put them into our website, put them on our website or wherever it is, and then I will do them immediately. I can do the whole thing. I'll do the whole thing. I'll do the whole damn thing. You just made me excited. I like ordinary differential equations. Let's do it. We'll do some partial ones eventually. Okay, we have this number e. Now what am I going to do with it? Now I'm going to say, let's find the derivative with respect to x of e to the x. We know the number exists. It's between 2 and 3, and we know its definition now. It's the number that has that nice limit, which is convenient, awfully. There's two other definitions that we could give, is that e to the 1 is equal to the sum from n equals 0 to infinity of 1 over n factorial. And we also know that e is, using L'Hopital's rule, the limit as n approaches infinity of the sequence 1 plus 1 over n to the power n, which is 1 to the infinity type. And my logarithm, and I'm going to use the inverse of this guy to find this one, coincidentally. But this seems somewhat roundabout. But e is also this. There's the other two definitions. I couldn't help myself. I need to get this stuff out. I don't want to get it out. I just need to. This is by definition.
It's like a reverse addiction.
Yeah, it is. This is how Bill Burr describes it. People don't become comedians because they just want to. They need to yell at the world. They need to do this. This is the limit as h approaches 0 of e to the x plus h minus e to the x over h. We're going to tell a story about, remind me, why do I use the h definition and not the a definition? Factoring is a lot harder than foiling. We'll get into that later. I've already sidetracked too much. This is the limit as h approaches 0 using an exponent law. Sum in the exponent is product in the bases. This is e to the x times e to the h minus e to the x over h. I'm specifically trying to show you now that in my mind, when you do this, I'll color code with a tablet pen eventually. But now I'm going to take this out. There's e to the x in both of them. So I'm going to factor that out. Also, h, I'm going to do two things in one because my brain wants to be lazy as a mathematician, and you don't, but I still want to point, I want to be lazy and wizard. I want to be lazy and have you understand the two moves I did instead of one in each step. So I'm factoring out the e to the x out of both terms, but then it'll be out here with a bracket, and the limit is 8, so I'm going to move it right outside the limit. Okay. And now where did that go by definition? Oh, I pointed at the other two definitions. This is 1. So the derivative of e is itself. Oh, I hear my daughter. It's alive. It's alive. Or fuck, it's Tim. Frick, it's Tim. PC bro, as soon as you laugh a little bit, he doesn't censor my F-bombs once in a while because I put him on he was playing the Legends of Zelda 2 the other day. And he's like, oh, it's a lot harder once you're actually talking. It's hard to not swear. It's like, yeah.
When you're in the hot seat.
Yeah, it's harder than you think. Hey. All right, so now I want to know what the derivative with respect to x of a to the x is. And then I'm going to use the inverse law. If y equals e to the x, if y equals e to the x, that's if and only if ln, which is the shorthand for log base a, ln of y equals x. And we have cancellation laws. Once this is the inverse, this means that a logarithm that touches e is going to go away in the domain, but I won't get into it. And when you make these guys touch in the exponent, this will leave you x in the domain of the function. Why do I want that? Because I'm going to do, the move is, they tell you the move and you nod at it, but what I wanted to start doing also is do a whole series where we do this. You have to write it backwards. I have x. I can now, and that's what I'm about to do. Because of this rule, I'm about to write it as e to the ln x. And you're like, where the hell did it come from? I just used the rule, but I'm using it in reverse. I have an x, and I'm going to do that to it immediately. So this is, I'm not taking the derivative yet. This is the derivative of a to the e to the ln x. And everybody says, what did you, yeah, that's why I did that. I showed you first what I was about to do.
That was a well-phrased question. Yes, very well phrased.
Also, do I want to use that one? No, I used the wrong one. Do you see why? Because I want to use the log law and I got excited. But also, the other cancellation is this one. X is equal to, you can also do the natural log of e to the x. No, I did the right one, didn't I? Yes. Now I confuse myself. Oh! It's this one, and I put it in the wrong spot. Oh, that was good. So I did this. Let's backtrack that, because I was talking and being pedantic. And then that's where pride comes before the fall. Pride comes before the fall. So this guy should go here, is what my brain just saw. I'm trying to give you a window inside. You don't want to see the rest. So this was correctly, this should be e to the ln a to the x, because I want to use the other exponent law I was going to use. They tell you if you have a natural log of x to the r, that guy will become r ln x, and you can take it out. And I specifically have started doing that. I've changed the notation. The rule is what I'm looking at, not what I call this or this. So I have these things. What does that say? The rule is the exponent on the inside becomes number on the outside. That's the rule, not what I called them. This is equal to the derivative. I'm still not taking the derivative. Usually I don't put it inside there, but I guess we're stirring the pot anyways. Now what I'm going to do is take that out. This is e to the x ln a. Now ln a is a number. Now I put brackets to show you that now what I'm going to do is take the derivative of e, which is itself, but I have another function on the inside, so I'm also using the chain rule. This is, by definition, e to the x ln a, which is what? This is this. Because I just have to go back through and do it in reverse. I'll do that, but everyone gets weird when I make that a to the x again. Put that back on, cancel, cancel, it goes away. I'll do it. Times what? The derivative of the inside. And derivative doesn't care about ln x. We can put that ln a because it's a number, and the derivative of this is 1. So that gives me equals, this is e to the ln a to the x, cancel, cancel, times ln a times 1, which gives me a to the x ln a. Good. Now what was I saying? A lot of things. So now if I want to do an integral substitution rule, I now know that a to the x primed is equal to a to the x ln a. Or if I call y equal If I call y equal a to the x, this means, let's use f of x like I did last time. F of x equals a to the x. This means f prime of x is equal to a to the x ln a. How do I use that to get the differential? We'll build the differential from that. The differential, therefore, would be f prime of x is equal to dy is equal to f prime of x dx. This is just unfortunate notation, which is equal to, what is it? A to the x ln, let's call it w2, you'll see why in a second. Ln a times dx. I don't have that, guys, so what am I going to do? I'm going to say dw over ln a is equal to a to the x dx, and then I can use this in the substitution rule. Then, yeah. So now what I'm going to do is have to cook up one. Oh, let's involve the one that we used last time. Let's do the integral of, should we use a or e to the x? I don't really care.
Let's do an a.
You want a to the x?
Let's
Okay,
do
he's gonna make me work. A to the x dx over a to the 2x plus 1. Can you see it?
Yep.
So now what they're trying to do is, they've given me who's g. G of x is 1 over 1 plus x squared. If I did g of a to the x, which would be g following a of x, what would I get? I would get 1 over 1 plus a to the x squared, which is equal to 1 over a to the 2x plus 1. So that's the substitution I want to make. Let's do that. Oh. Fuck, every summer. I got kicked in a rib in a karate tournament like 5 years ago. Every once in a while I pull or something or push and it just is like stab. You go to the doctor, like, I guess your ribs are going to hurt for the rest of your life. Doctors, what do they know? So what does this give me? I'm going to let w equal, what was the substitution? A to the x. Hopefully, I just did a whole rant on how to take the derivative and everything else. Therefore, dw you're going to see is equal to a to the x ln a dx, but I don't have ln a, so I'm going to divide by this. So dw is ln a equals a to the x dx. Business. What does that become? This becomes now, does the blue show up? Equals the integral of liquidation of all x's. All x's must go. That was a play on words. And every time I do that, it reminds me of the Japanese guy. They like the baseball in Japan. But there's a guy, he's like, that ball is out of here. He's like, that ball's so out of here. It's as out of here as my ex-girlfriend. It's out of here. Out of the park. Get me gone. Forwards. So all x's must go. It's liquidation of x's. What was this guy? This was dw over ln a. Let's move that over. Equals the integral. And then what was this? 1 over w squared plus 1. So now we're in the land of, this is 1 over ln a times the integral of 1 over w squared plus 1 dw, which puts me back on my lexicon, because watch it. That pole just jumped out at me.
We all saw it, yeah.
Yeah. It's like the trees when I walk down the street. Get out of here. I think you walked into that tree, sir. No. It's not a noose, it's a leash. That's a Tyler Joseph from 21 Pilots. All right, what is this one? Arctan. We know the derivative of arctan is 1 over w squared plus 1. So this is arctan of w plus c, and then for being a jerk, I just got an extreme foot cramp. I didn't hydrate properly. Sensational black weather. My foot hurts now. ln a. I squeeze in ln a over there, which is equal to, that counts as an integral, whatever that was, 1 over ln a arctan.
That was our 90th
a to the x plus c. There's 90. Is 91 prime? No, it has a 7 in it, and an 11, and a 13. Yeah. No, a 7 and a 13 for sure. All right, now what are we going to do? I did an integral, and then we're going to interrupt this regular programming because I prepared the wrong thing. And so I'm going to do a little bit of history of math now because I just killed a whole
Perfect.
bunch of time, and then you can interrupt me. We're gonna start making scripts and start organizing this crap. But Lorenzo's gonna give you a pitch on something, the history of channel and YouTube. We just made 2,000.
Yeah. So if everyone wants to check out the History of Math playlist, that's where these streams will be posted. I posted the link to that playlist earlier on in the chat, so check that out. But yeah, so that's been helping us grow. So please support us there as well as on Patreon, and continue to support us on Twitch. It's appreciated.
Yeah. We're all lowly sessional purgatory applicants trying to get out. I don't think you know how purgatory works. Shut up. I'm not Sisyphus. I got coffee grounds. I went all the way to the bottom of it. It's real coffee, not Tim Hortons. Sorry, Tim Hortons. Until you start paying us for advertising your coffee. I like it because I was born in Alberta, but it is kind of piss water. I didn't say we were going to stop drinking it. I had 2 today already. But that coffee was real and it had grounds in the bottom and it was stuck in my teeth. All right. We were doing, for the history of math, just for a little segment. Or do you want me to pause for a second? Oh, he's like, he just freezes. So then
This is all going up as one. This
okay,
is great.
we'll
Yeah.
chop up the history of math one too, just for the specifics. I still want this to be counted in the playlist, is what I'm saying. So
Yes,
go. Bab Elon, did I spell that right? Probably not. That's okay. What's that dot doing there? It's not. Babylon and Mesopotamia. All right, so what we've got is, last time we were talking about the geometric nature of things and then using the abstract algebra for these things. And what I was ranting right at the end was, you complain so much about algebra, but it had to be invented. So you should be going back to the real world type of things. And this is where you're going to see the rant where I really want to do practical things with mathematics, or root them in practical things and then carry out the abstract nation and generalize things if you would like to. But it should always be couched or phrased originally in some real world thing that I have to deal with. I should start modeling money because this has not been going good for me for the first 47 years. All right. So in that scenario, we want to talk about, I did the triangle numbers. And if you look at this rectangular array, this is 2 triangle numbers. The triangle number would be, as if you stack them in triangles, this would be 1, 2, 3. So this is n equals 3. And then they're trying to say how many triangles are in there. So in the last one, the segue that I did from there to today is, one I'm going to do is, what they would notice is that in the geometric nature, instead of having symbols for everything that we're inventing, we're trying to invent algebra. So this is the picture here. And then if you've taken Calculus 1, or I'm about to teach 2 of the classes at MacEwan this summer, I just made the course outlines and everything today, and we start next week already. I didn't realize. It's like, good thing I did that. Good thing I did that. This is the real world geometry, and you can have actual pebbles. And then we get a symbol that says this. They're going to say that when you can see it, let's color code them. 1. I realize that wouldn't work as good as I thought. 2. Maybe it will. We'll see how it goes. 3. So when n is 3, you get this. So when n is 1, how many pebbles are in the triangular array? This means that, let's call it T1 is going to be 1 for triangle number. When n equals 2, I see that I'm going to get 1, 2, 3. So that means that T2 is going to be 3. And then when n is 3, I see that T3 is going to be 6. And then what we want to ask is, we want to generalize that notion, and we go, well, what would it be for everyone if we just did 4 and then we just did ... n somewhere and we stopped? And that's how you generalize it there. I still got a triangle number and I want a formula for it in a closed form, and I don't want to have to calculate. And yes, I could calculate the fact that it's going to be, what could you say that the recursion is going to be? Could you see the recursion definition? Well, I know that I caught it. T3 is going to be what? T2 plus T1 plus N, or 3. So what does that say? I suspect, we can get into this later. I didn't want to get into this sidetrack tangent again. Tn is going to be the recursion. We're going to skip that because I'm going to show you with the picture that you can solve this with a bunch of algebra, but that would be a horrible mess because this is going to be a non-homogeneous second order recurrence relation. But this is Tn is going to be Tn minus 1 plus Tn minus 2, which is Fibonacci except for plus 3. That's why Fibonacci appears in Pascal's triangle and stuff. I want to segue into that too. I'm going to tone it back. That's the recursion. But now do you see, if I want to compute T100, I need T99 and T98 for those. But then for T98, I need T97 and T6. And then I have to compute all those all the way down. It's T's all the way down. T for turtle. I like turtles. I wanted to do the meme where we just have shorts where it's like someone asks me a math question. I'm just like, I like kitties. It's like, what? It's not what I asked. I like kitties. Just shout it out, kid, I guess. But it's turtles all the way down. So from this, what we want is we want to get somehow, this would be not a 3 anymore. This would be an N. Thank you. I'm correcting myself and then thanking myself for correcting myself. Shut up. I know, don't talk to them and put yourself in front of them. We're on live stream. These are jokes. I want the closed form. What does the closed form do? Does anyone know what it is? It's going to be n plus 1 over 2. Which also happens to be, if you look at it, this one was what? It's going to be the sum of the first 3 numbers. So Tn is also equal to 1 plus 2 plus 3, which is equal to the sum from I equals 1 to 3 of I. I can phrase it that way. There's a recursion. Here's this guy, and then I want the closed form. What do these two don't have that this one has? If I want T100 now, this is the meme that they have on the internet. If you get $1 more on each step and you climb 100 steps, how much do you get? 5,050, because you put n equals 100 in there. 100 divided by 2 is 50. 101 times 50 is 50. So then that's how much money you would get. I don't have to compute any of the other ones if I have the closed form. My point being, how can I get this just from the geometry? How can I get this just from the geometry? So let's go back here. What you need is insight. You need to think, in this case, think inside the box. Make a box, double it, they did cleverly. They think inside the box or outside the box, but view it slightly differently. And then if I look at this, well, this, if I called it that, this is T3 and this is T3. So I see that 2 times T3 is equal to what? Well, how many of them are there? What's the multiplication of the number of squares? Remember, the T is representing how many circles are in the diagram, or how many pebbles are in your diagram. Well, it's going to be 3 times 4. You're correct, Barney, but it's 3 plus 1 this time, not 2 plus 2. So then I see, oh, well, T3 is equal to 3 plus 1 over 2. Normally, you wouldn't write it like that. You would write it like this, 3 times 4, and then you want to write it as 6, 3 times 4 over 2, and then you cleverly, the students will write it as 12 over 2. Please stop doing that. This is 3 times 2 times 2 over 2, cancel, 6. See, there's primes in all of these numbers. Stop doing that. That's going to be other series that we do, efficiently computing things. Stop multiplying it together with your chooses. It's an integer. So should this be an integer every time. But what I want to see is also a pattern for the generalization. So I write it as 3 plus 1. So what do I think Tn is going to be now? It's going to be in that array. I double it, and I'm going to get n plus 1 over 2, which happens to be how many numbers are in the triangle. The sum from this is also equal to the sum from I equals 1 to n of I now. And so now I have a closed form. And how did I get that closed form? Very real world, very geometric. I got it from an array of pebbles. I got the horrible formula that you get when you have to do Riemann sums in Calculus 100. Good. That's still not what I wanted to do today. Now we're going to do what I wanted today and then end this charade. Charade. It's not a mirage. It's just magic. The other one I wanted to talk about in the Babylonians, they had in their sexagesimal, they had the square root of 2, and they wrote it as approximately equal to 1.245110. But this is in sexagesimal, which means this is 1 times 60 to the 0 plus 24 over 60 plus 51 over 60 squared plus 10. Yeah, some guy, there was no internet back then. There was no internet or anything back then. 60 to the cubed. This is approximation, which is fairly good in decimal notation. That approximately equals to 414222. And the actual correct to 6 decimal places is 1.414213. So they're not too bad. But this is the cookie, not the recipe. How did they do this is what I want to know in my mind. How the heck did they get this decimal expansion, whether they're doing it in base 10 or base 60? I'll switch back to base 10. That was another talk if you want to do base 60. Look it up and do all this pitching for the things that we need. Please give us money. Inventory sucks. That kind of stuff. Back to the math. I'm going to use square root of 2, and it seems like from this, when you look at the Babylonian tablets, I have a bunch of the old tablets that we showed last time, but you get a bunch of these tablets, and then they're trying to transform them, and they're all in cuneiform. What they realize is they had this formula. Long story short, where's the formula? This is approximately equal to, this is equal to what we have to find is the square root of a squared plus h. And then they knew that this was trying to use it as areas, etc. This is going to be approximately equal to a plus h over 2a. We can get into it later how they get this, but for now I just want to do this calculation, and I spent far too much time, and I have to do stuff with my daughter because that family over all, family über alles. Not Deutschland über alles. That's bad. Bad, Hitler. Bad.
That's
Kitty. It's like
history,
kitty. That's how my mind works. It's like kitty. Sparkly. So this is extremely useful. First of all, do you see that you're going to get a horrible square root? We want to do square root of 2. So the first thing I'm asking myself is in my notes, Lorenzo was in this history of math class. So I just say, well, if you take a equals 9 over 4, 3 over 2, even I don't know, I'm just going to show you how to cook it up. And if you take h equal negative 1 over 4, then that works out. Then you're just going to get this. And then I already start writing it out. I say square root of 2 is equal to what? And then I start putting in there, it's going to be approximately equal to, I put in the 3 over 2 squared minus 1 over 4. And then that's to the 1/2, et cetera, et cetera, et cetera. So do you see how so this is the question I wanted to start asking myself, and that's the epiphany I had today. And then he said this was working, and I prepared this. So I have this formula. It's from Babylon, and the normal people that get credited for this, I wanted to put that historically in there because Volker Runda says always, if you have this notion of something and it has someone's name, they weren't the first one to do it. It was the Babylonians a long time ago. So Greek guy I can't pronounce, Heron or Newton, and Newton is the most prevalent one who has this a Newton approximation, but it comes from them reading these old historical books from a long time ago. So how the heck is my question, even me reading back my own notes that I typed up, how the heck did I come up with this? And it does work out. The magic of the math is that math was math and it works out. But how did you come up with that? And then say if I wanted to do the square root of anything else, 37 or something like this, which is a fairly easy one, do you see what I'm trying to do? Do you see what they're doing? Well, they're like, well, I don't know how to compute the square root of that, but if I had a perfect square, say like the square root of 36, I know that that's 6, because that's the square root of 6 squared, which is going to cancel, and then I get a 6. So what they're going to do is they're going to be like, well, what if I take a perfect square plus a little bit of an h? So then I could write this as the square root of 36 plus 1. Oh, but then I'm in business because now I can use my formula and I can say that's approximately just going to equal what? That's all right. A squared, I should write it as 6 squared. So so that you see it in the formula. So now I know my A is 6 and my H is 1. So now what does that say? Well, it's approximately equal to 6 plus 1 over 12. Which again, now I want to hurt my brain, but we could do the long division. You do 12.1000, and then you can get your decimal expansion. How many times does that go in there? It goes into there 0. So I'm going to get 0, and I'm going to bring it down 100. So how many times does 12 go into 100? Who's the guy? 12 times 7 is 84. 96, etc., etc. You can get the decimal expansion of that once you have long division. My point being, let's go back to this one. I'm the same thing as what I did in my head, and then I typed it up, and you're doomed to live life forwards and then explain it to everybody else in your book backwards. So I got to start doing, I got to untrain myself of this too. So you're going to see me do it live in the next couple of years of me untraining myself to just regurgitate crap that I read in a book and then I already understood, and then quickly shorthandedly just said, oh, here's the few lines, because it's easier to just put that in my notes this way instead of actually explaining what the heck is going on.
So let me just take this time to say welcome to everyone rating us from Don Does Math channel. Thank you, everyone, for joining us. We're just doing more history of math.
History of math. Sorry, I'm running away now too.
Oh, and now he runs away, so I'm muting him. So it's now just Tim and I, and we are going to take this opportunity to plug our YouTube channel, which just broke 2,000 subscribers. So thank you, everyone. So check that out. I've posted the link to our History of Math playlist, but let me retype that into our chat. So please check that out and subscribe. Yeah, subscribe and watch our videos. Rewatch the lectures over and over again, please, everyone. And support us by continuing to watch. And I think, Adrian, you ready now?
Hey, I can't find it, so never mind. I'm not going to do it. Okay, so we'll just do this. I can't find it. I don't know where I put it. It's organized chaos, but sometimes I can't find things. Let's do that with root 2 now. So I want to do this to square root of 2, and I already put the curse of knowledge in your head, because can you remember what I erased? No. Okay, so...
Which?
Yeah. I already said A was 3 over 2 and H was negative 1 over 4. And so how did I know how to do that? I'm going to start with the number 2, and then I want to somehow involve this into what I did. So what can I do? And what did I want? I want to write this as a perfect square, because if I look at, first of all, if I'm reverse engineering, then I said 3 over 2 is what? 9 over 4, which is what? And X, this is 8 plus 1 over 4 using long division, which is going to be 2 times 4 plus 1 over 4, which is 2 and 1/4 is what they notice. So if I had 9 over 4 squared, I would have 2 plus 1/4. And so what would I need to subtract that off? 1/4. So depending on how I want to do this, let's write this as 2 is equal to what? Once I figure that out, or I square this, or I reverse engineer, I'm going to say, well, someone would have to sit there and be clever. There are certain points in there where I don't know how to say, otherwise somebody was clever and said that once they had this formula, they wanted to figure out how to. This is a tautology, by the way. That is true. This is definitely true. There is a universe out there in one of the versions of multiverses that I was just watching, where there's a universe where just 1 equals 1 is there, and there's nothing else. So that it is still a tautology. 2 is equal to 2. So what I'm going to do is now do this to you, okay? Because I'm going to use my dirty trick. That is 0. Good. That still also doesn't change anything. And I know that 0 last time I checked was 1/4 minus 1/4. So we're going to squeeze that in there. Okay. So I've got 2 is equal to plus 1/4 minus 1/4. So now I haven't changed anything. Then what do I have to do? Then I have to say, well, how do I add? So now I know that I wanted that 9 over 4 to get rid of it, because I've lived life forwards already and I figured this out. So then I have to add those fractions. And so 2 plus 1 over 4, I'm going to use the other dirty trick. I know that I can multiply by 1 by anything, and I know that B over B is equal to 1. So that means that B over B times A is equal to A. I think that's the first time I've ever written that one out, but that's what the rule that you want. Do it this way, not this way. See, the Arabs, when I teach them, probably understand us a whole lot more because they're used to reading this way. So they're reading it backwards just subconsciously, I think. But write that backwards. When I have A, this is A now, I can just get whatever I want because I'm going to write that as 4 over 4. Now what is that? That's exactly 8 plus 1 over 4, which is 9 over 4. So doing that side calculation, I now see that this is equal to 9 over 4 minus 1 over 4. This is a perfect square, so that is 3 over 2 squared minus 1 over 4. Sorry, Lorenzo, you got the shorthand the first time I taught the class, but literally I made this crap up the night before half of the time, and then I went in there and I was like, I know how to do the history of math. I learned this last night at 2 in the morning.
That's the Marge Simpson approach. Just stay one lesson ahead of the student.
Yeah, that's all.
What year would you say about this is the era? This would be about 3000 BC or
yes,
so?
this is
roughly?
between, I have this
2500 to 3000 BC, I think, or a little older maybe.
The representation, this codex has a date on the back. This is 1750 BC. So 3,000 to 5,000 years ago, yes, is when they're reigning this. Yeah. Yeah, exactly. It wasn't Newton. It wasn't Newton. He did some stuff, I'm going to admit.
Yeah, a couple of things.
So now let's actually do the calculation. Let's see. And what does that say? And then I'm going to get into numbers and I'm going to be like, see you later because I'm not doing this and I'm totally uninterested now. So the square, true story. I'm going to use the formula right below it. Now we've pre-analyzed that. I know that the square root of 2, being clever, is equal to the square root of 9 over 4 minus 1 over 4. I'll still go fairly slow, which is now equal to a perfect square that I can square root minus 1 over 4. And then this is approximately equal to, using my formula, a perfect square plus another little extra h. So this is technically, let me write this out. I should remind everybody, this is the definition of subtraction. Subtraction is the square root of 3 over 2 squared plus negative 1 over 4. I was like, oh, that's the definition. B minus A is equal to A plus, or sorry, where are you going, A? This is not commutative. You can't just willy-nilly plus negative A, the additive inverse. Everything is addition. Everything is addition. So what is this guy? This, we're going to switch square root. We're going to Euler colors. Is that today or tomorrow? Tim will know. Is there an Euler game today? He's like, I don't know.
Is there an Euler game today, Tim?
Where'd that?
No, they lost last night, so they're going to have travel bans.
Damn it, I just lost that pen. That pen just went in the ether. That pen just went the same where time goes. I don't know where it's going.
It went into a multiverse.
I went somewhere in the corner. Don't put your leg in there. Well, I'll put something in there later. We'll see. This is approximately equal to 3 over 2. Did I do that right? Yes. 3 over 2 plus what? The negative 1 over 4. Over 2 times A, which is 3 over 2, which is going to cancel. And then now you guys tell me what that is. Did I do that? I've got a better method for it. Okay, I'll do it. What is it? I just looked and I cheated. And I was like, okay, I'll do it now that I read it off the screen. This is equal to, the 2's cancel. I was still doing it, and then I told you, as soon as I get the numbers, I don't care. I just cracked open how the Babylonians did it. You can do this for any number. Should we try it with roots? Oh, just a second. That will be interesting because I have no idea what the answer is. Let me get into my serious, hold my beer stance. This is 3 over 2 what? Minus 1 over 12, which is what? One of the first approximations you get, which is 17 over 12. Remind me next time we do the history of math, we're going to use the other one that we used last time, and you get 17 over 12 in the other approximation using the intervals.
So what was the thing that you said in your mind that you were going to do because you have no idea what it is?
Oh, yeah, that one too. Good. I already forgot about that. I was like, already fucking next one. Let's do that with 3. I don't know what the answer is. What's the square root of 3 going to be? It's like no one wants to help anymore. All of a sudden, it's like I threw myself,
all you got the
threw myself
microphone.
under the bus. See, this is the thing where I was like, let's actually try that because I don't know. So what we want is we want an A that's a perfect square. And then we want, so what can we do? What we did with the other one was, can we use 4 over 3? What's 4 over 3 squared? We need a number that when we add it, we get a perfect square. So what I want is this. Oh, I see how we can do this. No, I don't. I'm going to mimic it. Let's mimic the 2. This was what? It was 2 times 4 plus 1 over... Oh, no, that was still the 9/3. Okay, so now, yeah. We have to be... See, this is the process of being clever and cooking up a perfect square minus something. Let's do... Okay, let's do the one more than that. What is 16 over 9? Let's try this. They used the 3 over 2 squared, which is a 9 over 4. So I'm just using... Tom! Tom came to say, Tim, there's a cat. There's seriously a cat. Is everyone else seeing the cat? He went that way. He's like, where? I don't see a cat.
no cat.
Threw me under the bus.
No cat.
Kitty. Kitty came to say hi just a second. Where are you?
Oh my god, there's always cats here.
There's always
Everyone
cats.
knows. Yeah, there's like 6 cats here. Cats just wander in from off the street.
Yeah, some of these cats. There is that one where he tried to bite me. It's like, this one's not even my cat.
Comes in, feed me, and then
That
bites
guy
you.
was cool. That guy was cool. Anyways, there's Tom. So let's try the next one. So what is that? If I get that, I want that to be a 3. Is that what I wanted? So then what am I going to do? So this is actually going to be what again? This is going to be, let's divide the 16 into the 9. What are we going to get? We're going to get 1 times, 1 is a perfect square. 1 times 9 plus 5 over, no wait, 60, yeah, that's right. Did I do that right? Yes, which means this is 1 plus 5/9.
Should it be a 7 instead of a 5?
Yes, see, I told you, way to go. Shush. I can't add and subtract. That wasn't even a 16, it's not even a hard one. God damn it. Zip, zip, zip. Yes, I need Lorenzo to feel good about himself once in a while.
That one was actually Fembox, man.
Okay,
I can't
fam,
take credit.
I got to keep the audience paying
There's
attention.
written proof that it wasn't me, so I can't take
Yeah,
credit for it.
And I also, I need to just see if the audience is still listening. That was an intentional mistake.
Of
That
course.
was
You know,
clearly.
I had a teacher in high school that used to do that stuff on purpose, and holy crap, I still get PTSD from it a little
I joke about it because I had an East Indian office mate at the U of A, Jatinder Bajpai, who used to do it too, and I was like, that's like gaslighting in your math class. We're trying to pitch this as fun, and you're gaslighting them. Okay, so then, why did I pick 16? So what I wanted was, what were we trying to do? This guy trying to find a perfect square with just the next number. It's not so easy until they've cooked it up for you. So what's the 3 over 2? Is that going to be right? No. So 16 wouldn't work. I need a perfect square over a perfect square. Let's try it because I only got...
This one's pretty close, isn't it? Because that would be 1.77 repeating, which is pretty close to root 3 as 1.7. Yeah, exactly.
Okay, so let's try it. Yeah,
Yeah.
okay. You're already, yeah. Okay, you're more confident than I was. So this is going to be so what do I have to do? This is what we're going to get, right? And then we have to subtract off this guy. 7 over 9, not 5 over 9, you idiots. So then this is going to be approximately now, what was it? What did I say? This is going to be 16 over 9 plus 7 over 9 minus 7 over 9, which is approximately equal to, what did we get? We get the square root of, let's match it again, that's 4 over 3 squared. Right? minus, yeah. I was staring at it again, which is approximately equal to the same thing. And then I'm definitely walking away now after this one. 4 over 3 plus, what was our h, negative 7 over 9 over 2 times 4 over 3. So clean that up, and then you're going to get what Lorenzo said correctly. He didn't correct me on the other one, but he did say the other thing. I say a lot of things. I'm the king of France. I'm the king of France. I'm the king of France. No one has phoned me about being Dauphin yet.
So just a last comment there if you want to read that real quick.
I mic dropped already. No, mathematics is the aristocracy, I can't say it, me fail English, the aristocracy of the sciences, and the aristocrats. Mathematics is the aristocrats of all the sciences, and number theory is the queen of all mathematics. This is a quote. He probably pronounced it better, and in the Deutsch by Carl Friedrich Gauss. Now I'm out.
Oh, there you go. Yeah. All right.
You haven't met, everyone says, I never used to really like math. It's like, you haven't had me yet. Let's see. Let's go. I'll see you tomorrow.
So, yeah. Just really quick, I will plug the Discord.
You
Join
do
us
whatever,
on Discord.
do whatever you want. I'm out.
Here's our Discord, so join us on there. We're trying to be a little more active on it as well, so feel free to ask questions and whatever you like. Post some memes, and we'll just discuss math and some ideas. And then you can also visit us on our Patreon. We do have some books on Patreon. Now, I know there's a lot of material out there on learning math and statistics, but if you want to support us on Patreon, you'll be supporting this channel so that we can do what we love doing, and we've made it our goal to bring this to everyone around the world. So please feel free to pop in there, and also check us out on YouTube as well. All right, thank you everyone, and we'll see you next time. I think Tim is doing statistics on Saturday. We might be doing something tomorrow. It might be open discussion and gaming. We'll see. We don't know. We'll play it by ear. But definitely it'll be statistics with Tim on Saturday, and then more history of math on Sunday. All right, thank you everyone. Good night.